Hi guys, today we're going to be talking about the Earth's structure and shape. Well, we know the Earth is a sphere. Why? Why is it a sphere? What force pulls the Earth into such a tidy, compact object? Well, it's also the same force that pulls you down to Earth's surface. Gravity. It keeps mountains on Earth from getting too high. It certainly keeps buildings from being able to be built too high. Gravity. Any astronomical body massive enough will have the same basic shape of a sphere, because a sphere is the most compact shape possible. On Earth, it's so massive we can't have mountains all that big. Mars, surprisingly, is much smaller compared to the Earth. Mars has the biggest mountains we've seen in the solar system. How can that be? Such a small thing has such big mountains. Does that make sense? Of course it makes sense. Mars, being smaller, has considerably less gravity. So the mountains on Mars can get bigger. A mountain getting that big on Earth, the gravity would pull it down. It would actually sink into the crust. It can't get too big. Here are some moons of Mars, Phobos and Deimos. Now, how big do you suppose they are? Are they spheres? No. So can they be so big? No. They don't have enough gravity to pull them into spheres. These are tiny little asteroids caught by Mars, and they are tiny indeed. They are potato-shaped. Anything like this cannot be very massive at all. Well, what other forces act upon the Earth? So actually, Earth is an oblate spheroid. Oblate means it's a little squished. Now, why would it be squished? Well, we know it's squished. We've taken the measurements. It looks like a perfect sphere from space, but taking the measurements, the polar circumference is actually less than the equatorial circumference. It bulges at the equator, okay? And that's because the Earth is spinning. The spin makes the equator bulge slightly. And we can measure that the gravity is slightly less at the equator. Now, why would it be less at the equator? Well, at the equator, because it's bulging there, you're actually farther than you are from the center of the Earth than you are at the poles. So being farther from the center of the Earth, the gravity is a little bit less. And we're talking a very little bit less. You wouldn't notice it. You need a good scientific instrument to be sure of that. What is some evidence for the Earth's shape? Well, photographs from space clearly show it to be a sphere. Astronomical observations. Polaris, the North Star, is positioned almost directly over the North Pole. It's always in the same place in the sky, and the stars seem to rotate around it. At the North Pole, Polaris would be directly overhead. As you move away from the North Pole, Polaris gets lower in the sky until at the equator, it's right on the horizon at 0 degrees. This shows the Earth to have a spherical shape. So now notice, your latitude at the North Pole is 90 degrees. Polaris is 90 degrees above the horizon. Our latitude is at 42 degrees north latitude. And if you look at Polaris and measure it, Polaris is exactly 42 degrees above the horizon. So the altitude of Polaris above the horizon gives you your latitude in the northern hemisphere. So look at that photograph from space. Earth is a sphere. So if we use the North Star as the example, someone in the North Pole looks straight up, while someone in Richmond looks at an angle to see the North Star. Where does someone in the Southern Hemisphere look to see the North Star? Right, they cannot see the North Star. Why? The Earth is in the way. This is what stars look like when you take a long exposure picture of them. How long would it take the star to go completely around? Well, 24 hours. So you could see the arc, and by measuring the arc, you could find out what part of a day that camera was open for. Look at these. So how long was this camera open for? When you look at it, you divide it, so a quarter would be 6 hours. This looks like it's a little more than an hour, probably less than 2 hours. If you look at shadows cast by the sun on the Earth, this was done by a gentleman named Eratosthenes about 2,500 years ago. He noticed that on a particular day, the sun was known to shine right to the bottom of a well. Therefore, the sun must be directly overhead of that well. There is another spot where the sun did not shine to the bottom of the well, but rather made an angle to the bottom of the well. That angle was 7.2 degrees. 7.2 degrees is 1/50th of the way around the Earth. So he realized if you could measure that distance from here to here, that distance multiplied by 50 would give you the circumference of the Earth. So he went ahead and he measured that. He got troops to march, and their measurement multiplied by 50 gave him a reasoned idea of the circumference of the Earth. Over 2,000 years ago, they knew not only that the Earth was a sphere, but they knew roughly the size of the Earth. Pretty amazing. Continued evidence for the Earth's shape. Well, all the sailors knew that Earth was a sphere. The reason? Well, when you're sailing, what's the very first thing you see of another ship? You would see the mast appearing out of the water. No ship visible whatsoever, but the mast seems to start rising up. As the ship got closer, you would start seeing the rest of the ship. So how do you look for other ships on the horizon? You send someone up to the crow's nest at the very top of your own mast, and they're looking for any other sign of a mast, which would indicate a ship below the horizon. Also, on the next picture I'll show you eclipses of the moon. The moon always casts a round shadow. The Earth always casts a round shadow on the moon, regardless of how the Earth is oriented. This can only be done by a spherical object. You might say, well, a disk could cast a round shadow. Yes, but the next eclipse, the moon's not in the same position, so how could you still cast a round shadow? Only a sphere always casts a round shadow. There's a picture of the ship sinking below the horizon, and if you wanted to be able to see the ship better, just send somebody up to a higher observing platform. Look at that picture of the 3 pictures of the moon going into the Earth's shadow, and you can see the Earth's shadow is in fact an arc, or part of a circle. So the stuff of the Earth is basically a huge ball of rocky stuff, and it's surrounded by a tiny little whiff of gas, and much of the surface is covered by an incredibly thin film of water. We study this stuff in similar proportions because we are really tiny. So this tiny bit of air and water really do affect us very, very much, even though most of the Earth is just a big ball of rock. Most of it is molten rock. So the solid Earth, on this ball of molten rock, the paper, for example, on this globe, the paper would be thicker compared to the globe than the lithosphere, the solid part of the Earth, is to the rest of the interior of the Earth. So the lithosphere is composed of rock with an incredibly thin layer of soil covering it in most places, water covering it in other places. The lithosphere ranges in thickness from 70 to 150 kilometers. It's thicker under the continents. Typical elements you find in the lithosphere in their order of their abundance. First is oxygen, silicon, aluminum, iron, calcium, then other elements. And these all group together to form minerals. The minerals all group together to form rocks. So if we look at this picture, what's the exaggeration in this picture? Sure, you could see the exaggeration in the picture would be the top thing. No way is it that thick. It's super, super thin. We exaggerate it so we can put mountains there and rivers and lakes and oceans and things, but it's super thin. That liquid part of the Earth is called the hydrosphere, and literally it's all the surface and subsurface water on the Earth, the water sphere of the Earth. The water covers 70% of the surface, has an average depth of 3 to 4 kilometers. It's made of hydrogen and oxygen, and it transports other elements extremely well. Water is amazing at how well it can transport other elements, which is why your body is mostly made of water, because chemical reactions work superbly in water. Now, most of the water we drink comes from rock under our feet. This is called groundwater. And groundwater is wonderfully clean, believe it or not. The water you take out of the rock is wonderfully clean water. If you have to get your water from rivers and lakes and such, you have to purify it before you can drink it. So the gas layers on the Earth, well, we call that the atmosphere. That's the shell of gases that surrounds the Earth. The atmosphere is layered, and each layer is defined on the basis of temperature changes that occur within it. For example, in the troposphere, this is where we live. The temperature goes down as you go up. Why? Well, the sunlight coming through the troposphere heats up the actual ground. So as you get away from where it's warm, obviously, it makes sense that it gets colder. And indeed, it gets quite cold as you go up in the troposphere. All the weather takes place here. All the clouds are here. Virtually all the water vapor is here. Most of the mass of the atmosphere is here. Nitrogen is 78%, oxygen 21%, other gases are approximately 1%. Carbon dioxide makes up a tiny, tiny fraction of the atmospheric gases, which is why as humans put more carbon dioxide in, it doesn't take a lot of carbon dioxide to start changing the heat balance of the Earth, because the heat balance is maintained with a tiny bit of carbon dioxide to begin with. After the troposphere, you have the stratosphere. And here, as you go up, the temperature actually starts warming up. Now, what could be the source of the heat for the stratosphere? Well, that's where the ozone is. There's a gas called ozone in that layer, and this is a gas that can absorb ultraviolet light. So by absorbing ultraviolet light, number one, it warms up. Number two, it makes Earth habitable for terrestrial creatures like us, because ultraviolet light is very damaging to DNA. So ozone absorbing most of the ultraviolet light makes the Earth able to be inhabited on its land surfaces. Above the stratosphere, you don't have any more ozone, so there's nothing heating it up. So as you go up, the temperature goes down again. Above that is the thermosphere. So here, you're in the realm of the solar atmosphere, so the temperature starts going up. But there's hardly any air. You would never notice the temperature's going up because you're not getting bounced into by many air molecules at all. Now, between each layer is a region of change. In other words, the temperature stops changing. It was going down, it's no longer going down. So we use the suffix pause in place of sphere. For example, tropopause, stratopause, mesopause. The thermosphere just gradually fades into the interstellar medium and therefore has no distinct boundary. If you look in your reference tables on page 14, you will see all the temperatures and you'll see the line connecting them in the atmosphere. That'll look a lot like this. And you see the temperature range. It goes down as you go up in the troposphere, it goes up as you go up in the stratosphere, down again in the mesosphere, and up again in the thermosphere. So all the layers are just defined by the temperature changes within them.